Alright guys, a chord is another line, or in this case a segment, that is drawn in relation to a circle. So we continue on with section 11.1, 11.2 notes. A chord is defined as a segment whose endpoints lie on the circle. And as you can see, we've created a chord here. This would be segment AB is a chord of circle O. All right. This segment has its endpoints on the circle, okay, meaning it intersects the circle at 2 points, whereas a tangent intersected a circle at 1 point. I like to always ask my questions, my students, a question like, what would we call a chord that went through the center of the circle? What would we call a chord that went through the center of the circle? We have a fancy name for that. We call it the diameter. Is a chord passing through the center of a circle. So basically, a diameter is a very specific type of chord. Okay, all right. Now, there's actually a lot of different things that we get when we draw chords, when we draw multiple chords. There's lots of different theorems and formulas. The good thing for us is that all of them are fairly common sense. We have some theorems and the converse of that theorem where we kind of think of it in reverse. Those are always true when we're dealing with chords, and we're going to explain a few of them here. Okay, so within a circle or congruent circles, congruent central angles have congruent chords. Now, just a reminder that an angle whose vertex is at the center of a circle, that's a central angle. Okay. Congruent chords have congruent arcs. Well, just a reminder that this, right here, this would be an arc. An arc is just a piece of the exterior, the outside of a circle, or a piece of the circle. Okay. And congruent arcs have congruent central angles. Really, I like thinking of this as almost like a cycle. Okay? Because if any one of these three things are true, then we know the other two to be true. So if what we're shown down here in example 1, it says that given BC is congruent to DF. There are two circles. This means that we have congruent chords. So we are told that in these two circles, these chords are congruent. We told it to us right there. What else can we conclude? Well, let's go back up here and think of this as kind of a cycle. And I just said that if one of these things are true, then the other two have to be true. So right now we were told that we had congruent chords, which means that we have congruent arcs, which means that arc BC would be congruent to arc DF. So from congruent chords, that leads us to congruent arcs, and it also should lead us to congruent central angles. And in this specific example, it would be angle O congruent to angle P. All right. Now, we could have replaced this given information with this part, and we then would have been able to prove that the chords and the central angles are congruent. Or I could have replaced this given information with the central angles being congruent, and we would have been able to prove the arcs and the chords congruent. Okay? All right. Fantastic. Let's skip past example 2. And go right to the back page, okay? So what we learned on the front page, we learned what a chord was. We learned that a diameter is a type of chord, a special type of chord. And then we learned how central angles, chords, and arcs are all interrelated, okay? Central angles, chords, and arcs. So chord, arc, central angle, chord, arc, central angle. Those are all interrelated. All right, great. Let's turn the page. All right, chords in relation to the center of a circle. All right, there's a couple theorems when we determine that. Okay, chords equidistant from the center are congruent. All right, so we have one circle. Here's the center of the circle. I'm going to draw two chords. I'm going to draw one here. I'm going to draw one there. Not too bad. Okay. How would we know that chords are the same distance from the center? Well, we'd have to be told that. Okay. So, remember how we measure distance from a point to a line. We've talked about that a lot. We would have to measure the distance in a perpendicular fashion. This is the distance between the center and the chord. And then again, perpendicular. This is the distance between the center and this chord. If these were congruent, okay, if we had the same distance from the center to this chord as the center to this chord, then the chords are congruent. Okay, same chords drawn here. All right. Now, we might not get tick marks. We could also just tell you, hey, this is a length of 8 centimeters. This is a length of 8 centimeters. You would then know that these chords are equidistant from the center. Therefore, they're congruent. And then the reverse of that is true. Okay. Congruent chords are equidistant from the center. So I'm going to come back up here and put a little double arrow here. Okay. So we can take away this kind of if here and just say if either one of these are true, the other is true. If I'm told that two chords are congruent, I would know that these were the same, the distances between the center and each chord. If I were told that the distances between the center and each chord were the same, I would know that the chords were congruent. It works in both directions. Remember, we call that the converse of a theorem. Okay? How about segments going through the center of a circle intersecting a chord? If a segment is perpendicular to the chord, then it bisects the chord. All right, so let me draw a circle again. Very similar to similar diagram to above. All right, has to go through the center. So if I draw a segment from the center of this circle and it's perpendicular to this chord, then it bisects the chord. Okay. You might see a question where you're given this information here, and we tell you that the chord has a total length of, 14. What you should be able to determine from that is that each part would be 7. All right? And if we read below, it also works forwards and backwards. Maybe I tell you that each part of this chord are equal, meaning this has bisected the chord. We would know then that it was perpendicular. Okay? Let's see where this would take place in a couple examples. Find the length of TR. Okay? So example 3 deals with both of these things. Here's what we see. Let's talk about what we see in this diagram. I see one chord, I see two chords, and I also see that those two chords are the same distance from the center. I see that segment TR is a distance of 9 from the center. PR is a distance of 9 from the center. Okay? So both chords are equidistant from the center. That's what I see, which means that they would be congruent. Right back up at the top. Chords equidistant from the center are congruent. So I now know that TR and PR would be the same. Okay. The question asked me to find the length of segment TR, so let's do it. Well, I also see a segment drawn from the center of the circle and intersecting a chord at a right angle. If the segment is perpendicular to the chord, it bisects the chord. Well, if it bisects the chord, and this part's 12.5, then this part is 12.5 as well. The length of PR would be 25, and we just said that PR and TR are congruent, so TR would be 25 as well. It kind of looks right, if you know what I'm saying? Equidistant, bisected, it looks like it hits it at the center. It makes some common sense if you really think about it, that if this was perpendicular to the chord, it would have to bisect it. Okay. An example 4, find the value of x in the circle. Okay. Well, again, let's figure out what we see here. I see 18 and 18, which makes that chord equal to 36. So what I see is that MK is congruent to PR. The chords are congruent. Let's go back up to the top. Congruent chords are equidistant from the center. Then X has to be 16. Because if these chords are congruent, they should be the same distance from the center. This one's 16 away from the center, making this one 16 away from the center. Okay? So different theorems leading to different conclusions, and you can see that a lot of these things are interconnected in a way, hopefully, that is common sense to you.